Chapter 13, we're talking about chance or probabilities, and this is part 2. So we're going to talk about the multiplication rule. The multiplication rule tells us that the chance that two things will both happen. So this is the key here. We're talking about two things both happening. So this means that A has to happen and B has to happen. So this equals the chance that the first will happen multiplied by the chance that the second will happen, given that the first has already happened. I know this sounds kind of difficult. It's easier to actually put into play. But notice that it says it's the chance that the second will happen given that the first has happened. So these are conditional probabilities. So for the multiplication rule, you have to use conditional probabilities. And it's a lot easier to use than it sounds. So let's try it out. For example, 108, a math department has 20 members, 3 of whom are women. If 2 members are chosen at random, then what's the chance that, so number 1, let's say what's the chance that they are both women? So we want the probability that we get a woman and then a woman. So the chance of getting our first woman, there are 3 out of 20. Then we're going to multiply it because we want another woman. But now I've already pulled out one woman. And when you think about this, if we're choosing 2 members at random, we're not going to put the first one back. We don't want to choose the same person twice. So now how many women are there to choose from? There are only 2 out of 19 women because we would do this without replacement. Anytime you're choosing people, it doesn't make sense to do it with replacement. Why would you want to choose the same person twice? Okay, so we have 3 out of 20 times 2 out of 19. And this, when I put this in my calculator, you're most likely to get it back as a decimal. Number 2, what's the chance that they are both men? So I want the probability of a man and then another man. So the probability of my first man, well, there's 17 men and 20 people. But then I've already used one man, so there's only 16 men. But I've already picked one person, there's only 19 total. So this would be 0.7157. What's the probability that the first is a man and the second is a woman? So we want a man and then a woman. So for our man, it would be 17 out of 20. Then we want to choose a woman. The first one was a man, so there's still 3 women, but only 19 people. So this would be 0.1342. And number 4, what is the probability that at least one of the 2 is a woman? And once again, there are 2 different ways that I can do this. I can do it the long way, or I can use the complement rule. Let's do it the long way first. So if I want at least one of the 2 to be woman, I could get a woman and a woman, or I could get a woman and a man, or I could get a man and then a woman. Now I think, nope, we haven't found all of these yet. So the probability of a woman and then a woman, that was number 1, that was 0.0157. Plus, now I'm looking for a woman and then a man. That's the one we didn't find, but if I wanted a woman, there are 3 out of 20. And then if I want a man, there are 17 out of 19. Okay, plus, and then if I want a man and then a woman, we already found that, that's 0.1342. And if I put that in my calculator, it's 0.2841. You might have noticed here that I used the word or and I added. And that seems kind of natural, but there is a specific rule that we're going to use in this class. So our overall guide is that if you see the words or, then you're going to add. And if you see the words and, then you're going to multiply. And so back to number 4. If we want the probability that at least one of the two is a woman, so we did it the long way, or we could use a shortcut here. We could use the complement rule. The complement rule says, well, the probability of at least one woman is equal to 1 minus the probability of no women. And how do you get no woman? The only way to get no woman is if you're man and man. And we already found that probability. The probability of man and then man was 0.7157. So if I put that in my calculator, I get 0.2843. Notice I get the same answer, except for I am off by about 3/10,000ths. And the reason why is just the rounding that I was doing on my intermediate steps. So either way, we're fine. Now let's try an example with some cards. So anytime we talk about a deck of cards in this class, this is what we're going to have for a deck of cards. Our deck of cards has 4 suits: hearts, diamonds, clubs, and spades, 13 denominations per suit, which means you have the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, and also the face cards Jack, Queen, King, and Ace. Hearts and diamonds are red, clubs and spades are black. And so hence there's 52 total cards, 26 are red, 26 are black. So your red cards are either hearts or diamonds, black cards are spades or clubs, and then for each suit you have the numbers 2 through 10 and Jack, Queen, King, and Ace. So for this example, we're going to deal 5 cards. And since we're dealing cards, this would be without replacement. It doesn't make sense to put your card back before you deal another one. So number 1, if the first 4 cards are hearts, what's the probability that the last card is also a heart? So when we think about this, so we've already drawn 4 hearts. So how many hearts are left? So if we were to make some notes, it might say something like 13 hearts to start and 52 cards total. Okay. But after drawing 4 hearts, there are 9 hearts left and 48 cards total. So I've drawn 4 hearts. What's the probability that my last one is also a heart? It would be 9 out of 48. Number 2 says, if the first 4 cards are aces, what's the probability that the 5th card is a king? Now notice here that we're not saying, what's the probability that I get 4 aces and then a king? I'm saying, you already know that you drew 4 aces. Now what's the probability that the 5th one is a king? So if the first 4 aces, what's the probability that the 5th one is a king? We haven't done any kings yet, so there are 4 kings total, see 4 kings. And because I've drawn 4 cards, there are only 48 cards left. Number 3 requires the multiplication rule, because it wants to know what is the probability that the first 4 cards dealt are all aces. The reason it needs the multiplication rule is that it's really asking what's the probability that your first is an ace and the second is an ace and the third is an ace and the 4th is an ace. So because you're asking for those ands, you have to multiply the probabilities. The probability the first one is an ace well, you have 4 aces to start with out of a total of 52. Times, now you want another ace, but you've already used one, so there's only 3 left out of a total of 51 cards. Now you want another ace, but there's only 2 left, and there's only 50 cards. And you want one more ace. Luckily, there's still 1 left out of your 49 cards. When you put this in your calculator, it's probably going to give you some kind of scientific notation like this, 3.69 times 10 to the negative 6. If you want to change that back to a decimal, it would be 0.0000369. And so that's our final answer, or you can leave in scientific notation. So notice there's a very small chance that your first 4 cards are all aces. Now, example 110, you toss a coin twice. What is the chance that, let's see, so number 1, both outcomes are heads. So we want the probability of a head and another head. Because it's an and, we're going to multiply. Well, the probability of getting a head the first time is 1/2, because it's either heads or tails. Each one is equally likely. Times, and then the second one is still going to be 1/2. Why didn't it change? The reason that those two probabilities didn't change is that coin flips don't affect each other. So let's make ourselves a note up here at the top. So the first coin flip does not affect the second coin flip. They are what we're going to call independent. And so this 1/2 and the 1/2, you could also consider them kind of the unconditional probabilities. They don't change based on what the first flip is. Because they're independent, we really don't care what any of the other coin flips give us. They're not going to affect our next coin flip. And so these are just unconditional probabilities. They're not conditioned on anything. Okay, so number 2, what's the probability that both outcomes are tails? So the probability of tail and tail. Probability of a tail is 1/2. Probability of a next tail is still going to be 1/2. So our total is 1/4. Number 3, the first is a tail and the second is a head. So probability of tail and then head. Lots of times I'll just abbreviate it as tail head. And the and is implied. So the probability of the tail is 1/2. Probability of the head is 1/2. Again, the first coin flip does not affect the second coin flip, so these probabilities do not change in any way. So we get 1/4. And number 4, what is the probability that at least one of the two is a head? So I could do this the long way. I could say, well, could be a head-head, or a head-tail, or a tail-head, and I could find each of those probabilities and add them up. Or I can use the complement rule. So the probability of at least one head is 1 minus the probability of no heads. And how do you get no heads? You have to get tail, tail. That's the only way to get no heads. So this will be 1 minus the probability of tail, tail is 1/4. So 1 minus 1/4 gives me 3/4. So we mentioned independence. Now let's read about it. So two things are independent if they don't affect each other. So for example, coin tosses are independent of each other. Rolls of a die are independent. Draws from a box would be independent if we're just drawing tickets or marbles or whatever you think. If you're drawing them out with replacement, they'd be independent because each draw doesn't affect the next draw. But they are not independent if you draw without replacement. Okay, so not independent if you draw without replacement, because the first draw will affect the next one. Also, two things are independent if the chances for the second, given the first, are the same no matter how the first turns out. Otherwise, they'd be dependent. So let's look at example 111 to put that into play. So if A and B are independent events, then the fact that A has occurred does not affect the probability of B occurring. So they don't affect each other. So let's look at these examples and see if they'd be considered independent or not. So if I tell you that a card is red, does it affect the probability of a card being a jack? Let's go back up real quick and look at our cards. So if I tell you that the card is red, does that affect the probability of it being a jack? There's 2 jacks that are red out of a total of 26, versus ordinarily there'd be 4 jacks out of 52. So let's go back to our page. So if red, probability of jack is 2 out of 26, which simplifies to 0.0769 if you make it a decimal. But overall, the probability of jack, if you don't consider anything, there are 4 jacks out of 52, and this also, if you change it to decimal, is 0.0769. So this means that knowing the card is red does not affect the probability that the card is a jack. So this means they would be independent. So for our next example, if we draw a red marble out of the bag and then we put it back, how does that affect the probability of drawing a second red marble? And does this affect the probability? No. If you put the red marble back, there is absolutely no effect on the next draw. So they would be independent. So now for our next example, if A and B are dependent events, so not independent, then if A occurs, the probability of B occurring is affected. So in this one, if I tell you that the card is red, does it affect the probability of a card being a heart? Okay, so flip back and look at our list of cards. Okay, so if you know the card is red, then the probability of hearts is 1/2, because half of red cards are hearts because they're either hearts or diamonds. But overall, the probability of hearts is 1/4. So knowing that the card is red increases the probability that it's hearts. And so these two things would be what we call dependent. And for our next example, if you draw a red marble out of the bag and we don't put it back, does that affect the probability of drawing a second red marble? Yes, because there are less red marbles to choose from now. And so that would be an example of dependent. In this example, in a standard 52 card deck, are the events drawing a red card on the first draw and drawing a red card on the second draw independent if you put the first card back before drawing the second card. So we're putting the card back so as to be with replacement. So you're drawing 2 cards. We want to know if you draw a red card on the first draw and then you put the card back, does that affect the probability of drawing a red card on the second card? It does not affect the probability. So really it doesn't matter what the first card was. because you put it back before drawing the second card. So this would be an example of independent. Okay, but for example 114, in a standard 52 card deck, are the events drawing a red card on the first draw and drawing a red card on the second draw independent if you don't put the first card back before you draw the second card? So this would be without replacement. And so because we drew a red card and we didn't put it back, there are less red cards to choose from the second time. So the probability is affected, and because they're affecting each other, they are dependent. Now that we've done some theory, how does this actually affect us? So let's do some actual calculation problems. So for 115, I roll a die and I toss a coin. What's the chance that the die shows a 6 and the coin lands on an H? So the first question to ask yourself is, do the die and the coin tosses affect each other? They shouldn't affect each other in any way. So we want the probability that we get a 6 and we get a head. So the probability of getting the 6 is, well, just 1 out of 6 because there's 6 sides, and probability of getting a head is 1/2. So our answer is 1/12. Notice again though that we didn't have to think too hard about those probabilities because the die and the coin do not affect each other because they are independent. So I don't have to worry about trying to find conditional probabilities. I can just use the simple unconditional probabilities. So for example 116, a coin is tossed 5 times. What's the chance of getting head, tail, tail, head, tail? So we want a head, and then a tail, and then a tail, and then a head, and then a tail. The probability of that first head is 1/2 times, now the probability of a tail is 1/2. Probability of a tail is 1/2. Probability of a head is 1/2. Probability of a tail is 1/2. When you multiply these together, it's 1 out of 32. Notice that every probability is the same because each coin flip doesn't affect the next coin flip. Okay. Number 2, what's the probability of getting head, 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 head? That seems like that would be unlikely to get all heads when you toss the coin. Let's calculate it though. So the probability of head, 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 head. Probability of the head is 1/2. Probability of your next head is 1/2. Probability of the next head is 1/2, 1/2, and 1/2, which gives me 1 out of 32. So even though at this point I'd already gotten 3 heads, that did not affect the probability of my next head. Or getting 4 heads did not affect the probability of getting the 5th head, because each coin flip does not affect the next coin flip. And so the probability is still 1 out of 32.